Okay. Ryan is one of the developers of Center. He has been working on molecular dynamics flexible fitting for several years. And again, if you have collaborations with cryo-EM people or you are doing experiments, maybe some of you, this is a very useful method. And that's a very good example of the methodology that is of great use to what is happening in experimental structural biology.
Yeah, so as Ahmad mentioned, I'm a programmer here, and I work on molecular dynamics flexible fitting. And this is maybe a little bit different type of application of MD than you've already seen. Whereas Ahmad mentioned, this is, instead of using MD as a tool to investigate your system, it's more of a structural biology tool to build and model your system. All right, so with molecular dynamics flexible fitting, we deal with two primary data sources. So with X-ray crystal structures that you get from like the PDB, you have a fairly high resolution look at your system, but because of the crystallization process, the structure that you get might not actually be in a physiologically relevant state that you want to investigate. On the other hand, with cryo-electron microscopy, you get a generally lower resolution image of your system. However, it's in a conformation that's closer to a physiologically relevant state because you're not doing the intense crystallization process to your system. And so what we would ultimately like is to have a high-resolution view of our system in full atomic detail, but captured in the conformation found in the cryo-EM density. And so what we can do is computationally combine these two data sources, and we do it through molecular dynamics, hence the name molecular dynamics flexible fittings. So just a little background on how we do this on the theory level. So with an MDFF simulation, we add to the normal MD potential two new terms. And so the first term, this U sub EM, is derived from the cryo-EM density map. And so what we can do is take your experimental density, and we can convert that density into a potential that we can feed into our simulation inside of NAMD. And so generally just this process, we define some sort of threshold, which we cut out a bunch of the noise, the contribution from the bulk solvent that's captured in the density map, and we invert the density so that you can drive the structure from regions of low resolution to, low density to high density. And after we create this potential, we feed it into NAMD, like I said, using something called the grid forces feature of NAMD. And then we can calculate forces from that potential that push each of the atoms from low density into high density regions. And we have a couple different ways of controlling these forces with a global scaling factor and per atom weights. And so the default weights that we use on each atom is their atomic mass, because that roughly corresponds to how well they're seen in the density map. So heavier atoms are forced more heavily. And so the end result is that we're pushing our system into the conformation captured by this cryo-EM density. The second term, this U sub SS, is a general restraint potential. I'm going to talk a little bit about those restraints. The primary one that we use in almost all cases, which is very important, are secondary structure restraints. Because we're adding these forces onto our system and contorting it, we have to be careful not to disrupt the secondary structure of our system, because these density maps are fairly low resolution. And so if you don't restrain your structure, the density or the potential is going to push the structure into all the little nooks and crannies of your density map, which could just be noise, and you're going to distort your structure. And so we can add in these restraints to our system. For proteins, we restrain the fine side dihedral angles. We can also do the same for nucleic acids, where we restrain distances between certain base pairs. And so this is just trying to keep your structure intact while you're doing the fitting process. And these restraints also have scaling factors, so you can make these more or less flexible For instance, if your starting structure has a straight helix, and in your map you see that it's kinked, you can lower the restraints on that particular helix to allow it to bend. And if you have others that you know are very straight, you can make them rigid. You can ramp up those restraints to keep it in place. So we have a variety of other restraints that we can use that just depend on the type of data that you have and the type of system that you're working with. Another common restraint that we use are cis-peptide and chirality restraints. This keeps our peptide bonds from forming cis-peptides where you don't want them, and also keeping the chirality of our side chains in the appropriate conformation. Normally, you don't really have to worry about this in normal MD simulations, but because we're adding in these extra forces, we can contort our system in some cases, and so we want to be careful not to introduce any stereochemical errors. We can also restrain entire domains in our system to keep them rigid relative to one another. So here we have the red domain and the blue domain, which are kept rigid amongst themselves, but flexible relative to one another and the rest of the system, because you just have this sort of hinge bending motion where you're keeping everything intact, but folding it back into place. Some systems that you may work on have non-crystallographic symmetry, and you can use that information to improve the fits that you get to your density maps by basically forcing all of your symmetric subunits to be an average representative structure and improving your overall fit to your density map. But these are sort of dependent on your particular systems that you're working on. I wanted to touch a little bit on the simulation environments that you can run MDFF in. The most basic would be in a vacuum where you have no water molecules, and because you're not simulating those water molecules, it's extremely fast because you only have the protein. Yeah.
Yes. So now with the new higher resolution driving structures,
yes,
new additional restraints to it, or?
So not so much new restraints, because as the maps are better, the map is sort of a constraint, so you're already getting the benefit of the higher resolution maps. So now, if you're looking at a 4 angstrom cryo-EM map, now you actually see side chains. So if you're adding those forces in onto your side chains in your simulation, you're already getting the benefit of the high resolution maps. Now, the high resolution maps pose their own issues, this type of methodology, because you have these very sharp potential wells. Your map is very well defined, and so this method can get stuck in some of those local minima where it's not supposed to go. And so we recently have some new variations of this workflow to overcome some of those issues. I'm not going to go into that today, but if you're curious, you can ask. So we can run vacuum simulations where we don't have any of the solvent, and this is extremely fast because we're not simulating those atoms, but it can be potentially inaccurate. And so you can see on this right, we have this plot where we're looking at the RMSD of a couple test structures of the ribosome in these different environments. And this is an RMSD to sort of a known validation structure that we're using just to see how good our result is. And so the vacuum, you can see in red, converges quite quickly, but is at a fairly high RMSD to the structure that we want. So what we can do is, like you would have in a normal MD simulation, you can put in water explicitly. Of course, now you're simulating all those extra solvent molecules, and on top of having to simulate all of them, you have an effect of viscous drag on your system. So you can imagine if you have a piece of your structure that needs to move through the environment to get into a piece of the density that it needs to fit, it needs to push all those water molecules away. So there's a drag on your system. So it actually takes not just more computational power to simulate because of the extra atoms, but it takes longer to converge because you have to push those water molecules out of the way. So you can see in black here, the explicit solvent calculation is very accurate. It gets to a very good structure, but it takes a long time to actually converge there. And so we have a trade-off. We can actually use implicit solvent where we approximate the electrostatics of the water molecules instead of putting them in explicitly, and sort of a compromise between the vacuum simulations and explicit solvent. So you can see that the implicit solvent converges quite quickly, basically the same amount of time as vacuum because you don't have the viscous drag, but it's a little bit more accurate than just doing a vacuum simulation. Now I will say that in general, when you run MDFF, you can get away with just vacuum simulations. We're different than normal generic MD simulations because we have all these constraints on our system, like the secondary structure, the map that we're fitting to. Your structure isn't going to fall apart and fly around. And the end result of one of these fittings is a structure that you're generally going to take and do more investigation with MD anyway. So you can take that final structure, solvate it, and then work out, the last little issues in the structure. So as a software, MDFF is in both NAMD and VMD. It's used together in these two programs. And so we use VMD, which I guess you'll hear more about tomorrow, to set up our simulations, to prepare them, and then we actually run the simulation in NAMD, again using the grid forces feature of NAMD. And then we can use VMD again to visualize and analyze the resulting trajectory that we get. Because MDFF is software in both NAMD and VMD, all the features in both those two programs are available to us. And so anything that you want to use in NAMD while you run your fitting simulation, you can use in principle with MDFF. Yeah.
So you can use VMD or NAMD to take the MRC map from the primary M and change them to the potentials?
So you use VMD for that, yes. So I forgot to mention the map processing, but VMD will actually convert the MRC file to a potential and do all that, yeah. The actual fitting time is obviously dependent on the size of your system, the quality, what your system looks like, but we generally need a very short amount of simulation time, much shorter than you need for an MD simulation to equilibrate. We generally do it in less than 1 nanosecond. So these are pretty fast simulations in general. And as input, you only need a PDB, PSF, and a density map. So the same sort of things you would need for a normal MD simulation, except obviously you need a density map to fit it to, and you get the same sort of output where you have an entire trajectory coming out of an MD. So instead of having just one final good structure, you really have an ensemble of structures that you can then analyze for the best fit or best quality model that you got out of your simulation. So MDFF can work on systems that are very small, all the way up to hundreds of millions of atoms, because again, it's part of NAMD, so anything that NAMD can work on, which is in principle structures of any reasonable size that anyone's doing today, MDFF can also run on them as well. We generally shoot to work with 3 to 15 angstrom density maps. That's because anything better than 3 angstroms, you don't really need a fitting technique like this. You can just build your structure in directly to the density map because it's so well resolved. And anything worse than 15 angstroms, you don't really benefit from the flexible nature of MDFF over something like just rigid body docking because there's no information there in the density map really. You can run MDFF on laptops all the way up to petascale supercomputers. Again, this is dependent on your system size, but because this is just NAMD and VMD, it should run on any software or any platform. And because you don't need a whole lot of simulation time, you can sometimes get away with running these simulations completely on your laptop. We have a fairly new graphical user interface for MDFF inside of VMD. So if anyone does the tutorials, which I'll mention a little bit more about later, some of it shows like command line arguments, which is a completely valid way of going through MDFF. And I highly encourage you to do that because you get a feel for how it actually works. But we do have a new graphical interface that makes setting up and analyzing these simulations a lot easier. And so one cool thing that you can do with the graphical interface is something we call interactive MDFF. And what this allows you to do is actually watch your simulation happening in VMD. So you connect a VMD to your running NAMD simulation, and VMD will show you what's happening in real time. And not only can you view that simulation, but you can also pick specific atoms and pool on them, and you can add in your own forces to manually manipulate the structure. And this is a example of doing just that. And you can do this to sort of use your own expertise as a modeler and on your specific system that you might know a lot of structural details about intuitively. And so you could just help the simulation along and saying, all right, I know this helix needs to go in that piece of density, so I'm just going to help it out and drag it over there. And it can allow you to overcome issues if you have like a complex map where the structure is getting stuck, or if you just want to speed it along. This is a really nice and intuitive way of accomplishing that. And you can analyze these in real time while the simulation is happening. So you can see if you dragging the structure to wherever you want is actually helping the fit or harming it. And this is a cross-correlation that tells you the quality of fit between your structure and the density map. And here you can see it's improving as the simulation progresses. So again, just briefly mention how one way that we analyze the quality of the structures that we get, this is with cross-correlation, where you can create a simulated density map out of the structure that you get and compare that density map through Pearson correlation with the experimental density. And that gives you a general approximation of the quality of the structure and how well it fits to the map that you have. You can do this for local pieces of your structure instead of just one global correlation. So you can say, okay, this helix is fitting well, this helix is fitting bad. And we can do this using the timeline plugin of VMD, which has many different types of analyses. In our case, we're looking at correlation. And so the y-axis here are the residues of our structure, and the x-axis is actually the trajectory, the frames of our simulation. And so you can see as the simulation progresses, our regions of poor fit, like here, which are outside the density, are improving to green, getting a little better, and finally the blue, where they're completely fit inside the density. And so we have various tools like this that inform you of whether or not you've gotten a good structure. You'll hear tomorrow, if you haven't already seen the email stuff, about cloud computing on Amazon. And I just wanted to point out that MDFF is a very good use case for cloud computing because, again, unlike MD, where you might need to run for hundreds or more nanoseconds, we're only looking at maybe 1 nanosecond. And so that is very doable for very cheap cost on the cloud. So here, this is actually replica exchange simulation of MDFF. So this is even more than you would normally do for a basic MDFF simulation, and it still costs less than $1. So keep this in mind tomorrow when you run MDFF.
And by the way, Ryan was the one working on this adaptation of our software to Amazon. So the fact that we'll be using tomorrow is because of him and his work. So, and if something doesn't work, it's compared to him. So.
Yeah, so I'm going to be around both today and tomorrow. So tomorrow, so if anyone already has questions about cloud stuff, you can already ask me later. So I just wanted to wrap up and say that, so MDFF is a sort of generic workflow that I've shown here, but because you have, again, all these features of AMD and VMD, which many of you probably have yet to learn, you can adapt this workflow to any system that you might have. So if you have a cryo-EM density, or I didn't show this, also we can work with X-ray diffraction data. So if you have one of those types of experimental data sources, you can adapt the MDFF workflow to your particular system. And so, this is evidenced by the fact that there are many publications that have used MDFF successfully, and they're on all sorts of systems that range all sorts of sizes, have nucleic acids, different ligands, all sorts of weird things. So if you are interested in running MDFF, I highly advise you to look at the publication list. We have sort of selected publications on the MDFF website and see if anyone has done your system already, and with different data or something similar, and you can learn the little tweaks that they did to make it work for them. And so we have a MDFF website on our normal KS website. It's under software at the top, and it says MDFF. And from there, you can get these publications that I just mentioned, the tutorial, other documentation like information about the plugin. And about the tutorial, I suggest if you don't know NAMD or VMD yet, that you do those tutorials first today. Don't skip the NAMD tutorial this afternoon and just go right to MDFF if you've never run NAMD before. But after that, feel free to take a look at the MDFF tutorial. It covers a bunch of different topics. And I will be, like I said, around this afternoon and tomorrow if anyone wants to run the tutorials and has any questions.
Even though we don't have a specific day for MDFF, you are free to choose which tutorial you want to go through. So if you are free to go through MDFF.
Yeah, that's one thing that people have said in our past workshops. Sometimes there's this weird idea that we're forcing you to do a specific thing. So we say, okay, NAMD tutorial is Monday, and then you have to do all the NAMD tutorial. That's not true. You can do whatever you want. It's just this is the order that we sort of advise in case you're new to all of this. So don't feel like you just have to work on it all afternoon.
Just feel free to go to select the tutorial that you want to go. If we can answer your questions, you are lucky, and we are also lucky. If we can't, okay, we are in trouble. But just feel free, and we will find someone that can help you, even the most advanced tutorials that you might have.
So are there any questions? That was a sort of a fast and not very deep look at it, but if anyone wants to run this, let me know, and I can show you a lot more information about the specifics.
As far as I know, that's a so-called standard procedure for MDFF. That is, after the molecular dynamics, you need to do another round of minimization, right?
Yeah.
My question is that why is that step necessary? In my understanding, for the MDFF part, the system will reach it once it reaches convergence. That will give you a system in the local, somewhere near the local minimum. But for the next step of minimization, we'll use a brute force to make it into a real local minimum. But that will sometimes introduce overfitting problems, right?
I mean, yes and no. So the problem is if you just take your final structure from the fitting, because it's an MD trajectory, it's not necessarily, you're looking at really an ensemble of structures that are wiggling around in some local minima. And so if you really care about getting the lowest, minimum point in that general area, you have to do something like minimization. Just because, if you look at the last frame, it's possible that, the sidechain wiggled a little bit one way and isn't, in the actual minima anymore. And so you can look at the ensemble of structures, minimize it. I mean, they're going to be very similar, but it's just because you're not getting the best structure at the very end.
So the point will be more like to handle with the steps and coefficients for the minimization, so that you can prevent overfitting problem.
Yeah, so you can do the minimization without any of the map forces turned on at all, or you can use it and then you can lower the forces coming out. I mean, you have complete control. But the idea is just that you're getting the minimal structure at the end. But again, because you're probably going to take this structure and do more with it, it's not that big of a deal because you're probably going to do more simulations anyway. So.
Yes. And about cross correlation calculations, you can set a threshold. But my question is, the algorithm behind it is that it will cut the local map out of the whole map and calculate the cross correlation, or still use the whole map, but to do something with the rest of the map to make them 0 or something.
So correlation is undefined if you have 0. And so it only cares about where you have the map. So it is sort of inherently cutting what you're looking at around the structure that you have. So you're only ever going to compare the envelope around your structure and whatever happens to be in that same envelope from the density map. Anything outside of that, you can't actually calculate a correlation.
So
And
that would
it's-
be based on the structure. If you define some region, it will calculate the corresponding map around this region and just cut it into the envelope and to do the cross correlation, right?
Yeah, I mean, it's not doing any cutting. It's just that it won't even,
Okay.
it can't even calculate it
Okay.
for regions outside. So it's only looking at where there's overlap. So if you have, a piece of your structure entirely outside of your experimental density, for instance, the number you get is going to be sort of meaningless because
Yes.
you can't really correlate that to nothing.
Okay. And I have another question. Is it possible to apply this MDFF only on part of the protein?
Absolutely. Yeah.
Okay,
So
so-
you can even have like if you have a full structure and you just want to fit a piece of it, you can only say attract these atoms to the potential. You have complete control over that. So you can say, and you can even do like say all the C alphas or the entire backbone, or I want the side chains in this helix, and you have complete control. So you can have your full system in there and just fit one piece while you're simulating the rest of the system.
To do that, you need to play with a grid file.
There's something called a grid PDB,
Okay.
which you make when you set up these simulations, and that just tells NAMD, attract this atom, don't attract this one,
Okay.
and so it's pretty simple to set
Okay, I
up using
understand.
NAMD's atom selection text.
Okay, thank you.
So this is like when you are fitting to a EM map.
Mhm.
So the EM map is having a lower resolution. So you force the atom to be there and then you minimize it to fit into the density when you move.
So yeah, I mean, so you are creating these forces from the density map, and then you're just pushing it down the gradient. It's sort of a blind way of going down the potential. So all you're doing is moving down this potential from regions of low density to high density. And so that's why you have to be careful when you're doing something like minimization or how tightly you're coupling the structure to the density map, because it is fairly low resolution. And it's just being guided blindly by that potential.
So the way of doing minimization will take them like similar to punching from the saddle point to the going to the local minimum.
Yes.
So it gives more information about the molten global state. That is the concept.
So what gives more?
So that actually we cannot fit the side chains or something in the density, it can be anywhere. So once we pull it, so there may be a steric class, we want to minimize the flow.
Yeah, I mean, there shouldn't be any like steric clashes because you're running an MD simulation already while you're doing this. So there won't be any severe issues. The final minimization that you can do is just a matter of simply finding that local minima at the very end because you have that sample. So
that's what I'm saying. When you do all the kind of sampling,
yeah,
and whatever the structures you have got, everything is punched.
you can do that. I mean, it depends what you. So at the very end, you take your structure and then you run a minimization on it. Yeah. I mean, it's all just NAMD, so it's whatever protocol that you've done, and it won't do minimization by default necessarily unless you tell it to. So it's completely up to you. Yep.
So, what if you have a ligand in your protein and you're trying to fit it to the cryo-EM?
Mm-hmm.
Because the protein will be interacting with the ligand as well as trying to fit into the cryo-EM.
Right.
So does it just take a longer time, or?
So, in general, the way the forces are being calculated, they will tend to overcome any other effects going on in the system. They're by default fairly strong because we want these simulations to converge pretty quickly. You can change all those constants so that happens, more or less. So if you don't want the map having as big of an influence, you can lower those forces. Or if you just want the ligand to, go into where it should, you can increase the forces as well. I will say, one issue that you'll have there if you have ligands is parameterizing those ligands because you are still doing an MD simulation, so you have to get the parameters for them.